Let me introduce Professor Yu Nengkun. He is now an associate professor at QSI in UTS. He received his bachelor's degree and PhD from the CS department at Tsinghua University in 2008 and 2013. And he won a Distinguished Paper Award at OOPSLA 2020 and a Distinguished Paper Award at PLDI 2021. And he is now interested in quantum computing. And let's welcome Professor Yu.
Thanks very much for providing this opportunity of talking more about my research. So thanks for the invitation. So the title of my talk is Quantum Max-Flow Min-cut Theorem. So the Max-Flow and the min-cut, this problem was initialized like 60 years ago by this very famous paper by Ford and Fulkerson. So the question is, let me introduce the question. So the question is studying the property of a flow network. So a flow network is a tuple, is G. G is VESTC. So V is the V and E together forms a directed graph. So V is the vertices and E is edges. So among all these vertices, there are two vertices: the source vertex S and the sink vertex T. And C is the capacity, such that for each E in each edge E, CE is greater than 0. So the intuition is just the material flowing through a transportation network. And the material is originally from the source and is sent to the sink. So it's like you can regard it as a water or traffic in the sense that like the train. So for this example, you can see that the source vertex is S and sink vertex is T. So from S there are from S there are two outgoing edges, from S to A and S to C. So the capacity are 12 and 7 in independent respectively. So and B and D goes to T and with capacity 15 to 6 or 2 and 8. So now let's define min-cut problem. So an ST cut is a partition that AB of the nodes. So AB, the union of AB is all the vertices, and with that such that S is in A and T is in B. And for any cut, its capacity is the sum of the capacities of edges from A to B. In other words, the capacity of the cut AB equals to the summation of all CEs such that E out of A to B. So for the previous example, if we cut A is just the set of S, and then the capacity is nothing but 12 plus 7. So because from this cut A, so things go out is 12 plus 7 is 19. And the min-cut problem is to find a cut with minimum capacity. So for this graph, or for this little flow network, the min-cut is the cut with S equals A equals to S and A. And you can compute that, okay, the outgoing capacity is 7 plus 6 plus 1, because now this 12 is not included because 12 is inside A. And 7 is outgoing, 1 is outgoing, and 6 is outgoing. So is 14. It's smaller. And you can verify that this is actually the minimum min-cut. And
excuse me. So yeah. In the previous example, if we choose the cut just to be A itself.
No, you cannot do that because you have to maintain that the source is in A. The source has to be included in A. So,
okay, thank you. Yeah.
Yeah. So we can that's the static property of the TensorFlow, and we can also study the maximum floor problem. So a maximum floor is, or an ST floor f is a function that satisfies for each edge E. FE is between 0 and CE. This is called capacity constraint. And for each vertex, which is not the source and not the sink, the summation of FE such that E into V equals to the summation of E such that E out of V. In other words, for any vertex which is not the source and the sink, neither the source and sink, so anything flow in must also flow out. So this is called flow conservation condition. And you can see this is actually a flow, an ST flow, because you can see for C, everything coming in is 7 and outgoing is 7. For A, coming in is 5, outgoing is 5. And for B, oh, I got something wrong, but sorry. Yeah. And oh, sorry, I think this should be 1. This 0 should be 1. So the value of the floor F is the value F equals summation of FE such that E out of S minus the summation of E into S. So for this graph, there's nothing into S, so just out of S. So it's 12. If you sign this as 1, then you can see it's correct. This is the flow. And the max flow problem is to find a floor of maximum value. And you can verify that for this, this should be 1, sorry. And the value of the max flow of this TensorFlow is actually 14. So it's 7, 7, 14. And the classical max flow mean cut theorem states that for any TensorFlow, max flow value of a max flow equals to the capacity of mean cut. Because you remember that here the max flow is 14, and here the mean cut is also 14. And moreover, for there's a flow integrality theorem saying that if every edge capacity CE is an integer, then there exists an integer maximum flow, in the sense that each FE is an integer. So these are the standard classical result. And when we study quantum network or quantum tensor network, so we similarly define that a floor network is a tuple that G is V STD. So the same that we have V and E is a directed graph with source S and sink T. And the capacity DE is greater than 0, but is also an integer. So now we do not call it C, but we call it D for each E. And it is generally not a real number or positive number, but an integer. And a tensor network is defined from a flow network where each edge E is given as a maximum entangled state, psi E, with dimension DE. And we can also define a quantum mean cut. So similarly, an ST cut is a partition A and B of nodes with S in A and T in B. And now the capacity of a cut is no longer the summation of the capacity, but the product of the capacities of the edges from A to B. Formally, capacity of the cut AB equals to the product of DE such that E out of A. So why is this different from classical? Because classical is some summation, but the quantum is product. Because when we put two maximum entangled states together, quantumly we just tensor them, and tensor them with dimension d maximum entangled state and dimension d prime maximum entangled state, we tensor them, the dimension becomes d times d prime. So instead of product, or instead of summation, we use product in quantum case. And the quantum min cut problem is to find that for a quantum tensor network, find the Qn. So find the QMCN. And we also want to define the quantum max floor. So the quantum max floor is defined by a tensor assignment. So for each node V, EV, we denote EV be the set of edges containing V. And we define that Vs is the tensor of CDE such that, okay, E is in ES, in the sense that Vs is the Hilbert space of vertex S in, and VT is similar. It's just the Hilbert space such that the sync point in. And the tensor assignment is that for any U is not S and not T, TU is just a linear map, maps Vs to a complex number. So given TU for all U, which is not S and T, we can obtain a linear maps from Vs to Vt, because we, in some sense, we assign tensors of any vertex, every vertex, not S, not T, and then contract them all. So the only left system is just the Vs tensor Vt. So we obtain a linear map beta, which is from Vs to Vt. And the quantum max floor is the maximum rank of beta over all tensor assignment. Because this linear map is a matrix. You can regard it as a matrix or a bipartite vector. So it's maximum rank of beta over all tensor assignment TU. So this was initialized by this Danny Caligari and Michael Friedman and Kevin Walker's paper. And the maximum rank is actually representing the maximum entanglement between the source and sink that can be generated by applying SLCC protocols. Because you can see any tensor assignment of in the middle of any vertex in U is nothing but you just apply some local operation and then drop the system. And in this paper, Cui, Friedman, Satar, and Stone and Minton's papers, so they show that, okay, quantum, similar as classical, quantum max floor is always smaller than quantum min cut. And so they provide a conjecture that for any quantum tensor network of G is in VESTD. So they define NG as another quantum tensor network, which is VESTND. And they conjecture that as long as n goes to infinity, the quantum max floor of NG equals to quantum max min cut of NG for any given quantum tensor network. So Matthew Hastings showing that, okay, asymptotically that conjecture is true in the sense that as long as n goes to infinity, quantum max floor of NG divided quantum min cut of NG equals to 1. Because the previous result saying that quantum max floor is always smaller than quantum min cut. So this paper used a random assignment of tensors to show this. So this talk, I show that, okay, for any quantum tensor network G, there are infinite many n such that quantum max floor NG equals quantum min cut of NG. So rather than use random tensor assignment, so we use this very simple protocol, quantum teleportation. So suppose A and B share a maximum entangled state, and C and D share a maximum entangled state, and B and C are together. Then B and C can perform quantum measurement, Bill measurement to generate an entanglement, maximum entangled state between A and D. This is quantum teleportation, or you can call it as quantum repeater. So another observation is that we can always map high dimension EPR into low dimension EPR by local operation. So it says if DE is greater than DE prime, and then we can perform measurement on one vertex in this edge to map psi E to psi E prime. So we use these two. The max floor problem becomes we want to just maximize the product of FSV. So this is FSV is what we want to assign. So FSV such that okay, this V amounts all SV in E. So SV is a vertex is an edge in E that outgoing S, and divide product of FUS. So FUS is also an edge, and it maps is just the assignment of edges going into the source. And the condition is that FUV times SVU is smaller than DUV, in the sense that because we have a dimension DUV maximum entangled state, we can split it into two. One uses for one direction, the other uses another direction. And another condition is the floor conservation condition, that for any V is not S not T, so the product of FUV equals the product of FVU. And since we're working with quantum, so we require that each FUV is an integer. So this is an integer programming question, and no one knows how to solve a general integer programming question. And so we just look at the TensorNet flow. So the idea is we just look at the the network flow with VEST log D. So we're not working with this integer programming with many products, but we want to work with plus and minus. So for a quantum tensor network flow, so we go from VESTD to VEST log D, and which changes the product into plus. And the dimension of D becomes the dimension of log D. So now we just try to solve this question. So we just consider GUV is log FUV. So we take a log for all the FUVs. And now the question becomes, we want to maximize summation of V such that SV is in G and GSV, subject to GUV and GVU all smaller than log DUV. And for any UV, so these two has at most one of them is non-zero. And we want that summation of GUV equals to summation of GVU for any V is not S not T. And GUV we know is positive number. So this is just the max flow of network flow VESTD log D, which equals to its mean cut by the classical max flow mean cut theorem. And then we can go back to define that F prime UV is exponential of GUV, which is also a positive number. We get a real flow of a tensor network, quantum tensor network. But this Not the end, because we actually would like to have an integer floor rather than a positive floor. So to do that, we first try to find a rational floor of tensor network. So as we see that we now have a positive floor or real floor of the tensor network VESTD, which equals to its mean cut, because for the mean cut, the log, we take the log and does not and then do the exponential, it does not change it. So in the case that every f prime uv suppose is a rational number, then we've already have a rational floor. Otherwise, suppose there is some f prime uv which is not a rational floor, then we just recall the condition. U and V must have some vertex which is not source, not sink. So we recall the floor conservation condition that product all FUV such that UV is the into floor and VU is outgoing floor. If there's some F prime which is not a rational number, then there must be another. So there must be some W such that F prime UW is not rational or F prime WV is not rational. And we can keep going. So now suppose in the first case, then we can find another maybe F prime KU or F prime WK, which is not rational, and so on. So turns out we either find a circle inside the network or a path from S to T such that each edge is irrational. Any questions?
No.
Okay. And then you notice that their upper bounds are all integers, because the quantum tensor network floor is given as this. So the upper bound are all integers. And we can round in to reduce the number of irrationals, because since we have a irrational path and the upper bound of each edge is an integer, and we can round in it to reduce at least the one, and does not change contradict to the capacity condition or the tensor conservation condition. So whenever there is some edge, the assignment, the floor from the real floor is not a rational number, we can reduce the number of irrational numbers into rational, at least one, and the tensor floor is finite, or the graph is finite. So by repeating this many times, we get an integer, not integer, but a rational floor. Yes. So using this, we get a rational floor, and from the maximum of rational floor, because you know that the rational floor is already with maximum is the maximum floor, so equals to the mean cut. So from the rational floor to maximum integer floor, so we can carefully choose an N and construct an integer floor of V, E, S, T, and D, and which needs us to use the floor integrity theorem. And then we can actually show that, okay, now we show that there are infinite many n's such that quantum max floor of Ng equals to quantum mean cut of Ng. And there are open questions. So open question is like for quantum tensor network, the original conjecture can be interpreted as for n, as long as n goes to infinity, quantum max flow of ng equals quantum min cut of ng. But we only show that okay, there exists infinite many n such that quantum max flow equals to quantum min cut. And so we also want to comment that the teleportation idea is not enough, in the sense that our idea cannot be used to show this conjecture that quantum max flow of ng as long as the limit equals to quantum min cut of ng. For example, is this. So this graph has four vertices, S, T, and this and this. And from S to this one, we have 2Q, 5Q. Suppose we want to show this, and we choose n to be a prime number Q. So we have 2Q, 5Q, 2Q, 3Q, 3Q. So you can verify that the min cut is actually 9Q squared. But for prime number, you cannot assign the integer program we given to show that okay, for sufficient large prime number, one can actually assign an integer programming such that an integer floor such that okay, the floor value is 9Q squared. So probably to show this conjecture, we need other ideas. Yeah, this ends my my talk. Thanks.
Okay, thank you.
Thanks. I hope it's clear.
Yes.
Is there questions from the audience?
Sorry, I may not so clear about the law of the n there. What's the law of n in ng? What's the law there? Can you explain again?
What did you mind to speak louder?
Okay, I mean the law of n in ng. Do you hear me?
No.
You not hear me?
I can hear, but do you mind to speak louder?
Okay, sorry. I mean the law of n in your
Yes.
ng and nd. What's the n there?
Yes, n is an integer number. So in the you can see here. So in the tensor network, so oh sorry, it should be here. Yeah, so now you can see for each edge, if the dimension is dE, then it's a d-dimensional maximum entangled state. So if we change it from dE to NDE, you can see here the definition of n is NDE. So in the sense that you replace you add another d-dimensional maximum entangled state between any edges.
You mean in any edge you add n times copy or?
No, not n times copy. N times copy, this will be d tensor n, but just given another n-dimensional maximum entangled state.
So how's the state living in the graph? You can just arbitrarily put n copy of them about n dimensional on it.
Do you mind to repeat?
Okay, sorry. Maybe I put the earphone. Is that louder?
Yes.
Okay. I mean, how's the quantum state living in the graph? So how's the n-dimensional state you mean living in a specific node?
How is the quantum state what?
I mean, can you explain again how's the
the law of quantum state living in the graph, so that you can add any n-dimensional state there you want?
I don't understand, but let me try to explain a little bit. So you see here, this is a definition of the quantum tensor network. So yes. we have a graph, and for any edge, it's just associated with the integer number, and the integer number is correspond to given a maximum entangled state between the edge. So this is the original tensor network. But if we change this d into nd, then it's nothing but we add another maximum entangled state of dimension n among all edges. So for instance, here you can see this is 7, then it's just a 7-dimensional maximum entangled state between A and S. Then if it's n7 or 7n, then we just assign another maximum entangled state of dimension n between A and S.
Okay, I see. So the maximum entangled state living between the nodes of certain edge, living
every edge.
And
yes.
when and how do they decompose into when they across a node?
What do you mean by decompose? There's no decomposition. So this A and S share the D dimension, and this A and B share 1 dimension, which is nothing, and this A and D share a D dimension, 6 dimension. So the total dimension of A here is just 7 times 6 is 42. So there's no decomposition.
Okay, I see. And another question is about how can you change the rational and irrational and real number in the state? How do you do that?
We did not change the rational irrational. We just prove that. So our goal is to show some integer programming, right? We will try to assign integers of the floor as a floor, and we do not know how to show that directly. So we just theoretically we prove that, okay, first we can have a real or positive floor, and from the positive floor from the real floor, so we find a rational floor. So this is all done by paper. Then you write it. Okay, you find that there's a rational floor, and afterwards for the rational floor, then you get a rational floor. Then you go to an integer floor by assign n to be very large, and such that it can just maps almost all the rationals to integers. Okay. So suppose you have a floor from A to B, which is 2/3, then you just assign some 3k, then you putting them together, it becomes like 2k.
Okay, I see.
It becomes integer.
So use the trick from rational to integer by the adding n-dimensional mentioning entangled state. Okay,
yes.
I see.
Yes.
So how's the flow in the state transfer? Is there any state transfer, or how's the flow in the state?
You just use teleportation, right?
Okay.
Just teleportation. So if you have an integer floor, then you can simply just perform teleportation to transfer this dimension to that dimension and eliminate all the rest instance.
Well, what do you mean transfer from this dimension to that dimension? What do you mean?
You can simply say that suppose A and B share a maximum entangled state with dimension 2, and C and D share a maximum entangled state with dimension 2. Then B and C are together. And then you perform a measurement, then A and D becomes share a dimension 2 maximum entangled state. That's it.
Okay.
So any integer floor correspond to such a protocol, you can see.
So you're not saying there is a real floor. It's just maximum capacity you can have
Achieve.
Achieve.
Yes.
Okay, I see. Okay, thank you.
Thanks.
And is there any question from the audience? If no, I wondering, is there application of the Maxwell mean cuts in the quantum analog Do you have any comparison with between quantum and classical?
Yes. So classically, the Maxwell mean cut is very useful, and almost everywhere, and like the traffic control and stuff, and a network capacity. I think quantumly we can this quantum Maxwell mean cut has the potential of, you can see. So it's origin from mass, right? You can see here. Yes. So it's trying to show the positivity of universal pairing in 3 dimensions in a sense. And as application, I think it's it can be used in the routing of quantum network, because you can see it. So so you have many nodes, and each pair of nodes could, or each sum of nodes could be connected, and with maximum entangled state, and then you want to distribute entanglement between the client and the server. Oh. Yes, I think this is one.
I see.
Yeah.
Thank you.
Thanks.
Any other questions? Okay, if no, let's thanks Professor Yu again for this nice talk.
Thanks very much.
好，于老师，谢谢您。
不用了，好，谢谢。
叶能坤，谢谢。这个工作蛮有趣的，继续把它完善吧。看起来那个 open question 如果解决，应该是这个 impact 蛮大的。
不知道怎么弄。
是，好，那个我们这边也有那个谁，国进做的 research 应该比较像吧？国进你可以看，你也可以想一下这样。
好。
好了，那我们改天聊，看看有機會，也許回澳洲一趟。好，有事聯絡，好，拜拜，謝謝，
拜拜。
那我們就接下去我們的 meeting 好。